holds even in the case when the measure of the entire space is infinite, as long as the space is sigma finite, and the following condition holds. So the remark says this. Uniqueness lemma still holds if the assumption mu1 of x equals mu2 of x finite is replaced by the following. There exists a sequence of sets En in sigma such that En is an increasing sequence, and the union of all the En is x, and mu1 of En equals mu2 of En, and they're both finite for every n. Right, so essentially you can replace finiteness by sigma finiteness, and then you have to have a sequence where the measures coincide. So we're not going to prove this. This was just a remark, and you're allowed to use this on the problem sheets or in the exam and so on. Okay, and the final theorem of this section is called the monotone class theorem. And the statement is this. So start with a set. And let A be a pi system on X. And let capital sigma denote the sigma algebra generated by A. And let this calligraphic H be a vector subspace of the bounded real functions on X. And assume that the following three conditions are satisfied. First, just the function which is constant 1 everywhere has to be in H. Second, characteristic functions of elements in A have to be in H. And third, every bounded real valued function on X, there exists a sequence Fn of functions in H such that sorry. Sorry, I'm going to write this third statement again. This was wrong. If f is a real valued function on X and bounded, and there exists a sequence Fn of elements in H such that Fn are non-negative, increasing, and converge to F, then F is in H. So that's the third assumption. So this says that any limit of an increasing non-negative sequence in H is still in H. So some kind of closeness undertaking limits of the space H. So these are the three assumptions. And then the statement is that the set of bounded sigma measurable functions on X is contained in H. Okay, so sigma came from this pi system A. Sigma was just the sigma algebra generated by A. And then the statement is that every vector subspace of the bounded functions, bounded real value functions, which satisfies these three properties, contains all measurable functions. And if you think about it, it kind of makes sense. You kind of can see why this would be true. Because if these characteristic functions are in H, and H is a vector space, the linear combinations of such functions are in H, which means that simple functions are in H, and then we're allowed to take limits of simple functions, and limits of simple functions are measurable functions, more or less. So it makes sense that such an H would contain all bounded measurable functions on X. And essentially that's how you prove this. Yeah, the proof is just a more elegant version of what I just said, basically. And it uses Dynkin's lemma and all the stuff we proved last time. So, the proof starts by defining a set D of sets, which, so D is defined to be all S in sigma, such that the characteristic function of S is in H. Okay, so by definition, D is a subset of sigma. And now, and in addition, we know that A is a subset of D because of this second hypothesis, right? Every characteristic functions of elements in A are in H, and D is precisely the set of sets where the characteristic functions is in H, function is in H. So this pi system A is a subset of D by assumption 2. Okay, and now the first step of this proof is to show that D is in fact a D system, We've seen the same strategy several times last time. So we showed that D is a D system, and then Dynkin's lemma will tell us something about the relation between D and sigma. Okay, so to show that D is a D system, we have to check three things. First, the entire set X has to be in D. But if you look at the definition and the first assumption says precisely that X is an element of D. So this is clear by the first assumption. Next, we have to show that if A and B are in D, and A is a subset of B, then we have to show that the set A minus B is also in D. Okay, but D was defined by properties of the characteristic function. So let's look at the characteristic function of B minus A. The characteristic function of B minus A, if A is a subset of B, then this can be written as chi B minus chi A. Right, this difference is equal to 1 only when X is in B minus A, and 0 otherwise. Okay, but now, and now this characteristic function has to be in the space H, right? But by assumption, this is in H, and this is in H. And we know that H is a vector space, right? So the difference between these two functions will also be in H. So the entire thing is in H. Because, so here we're using the fact that H is a vector space. Okay, but chi B minus A being in H just means that B minus A is an element of D by definition. So we verified the second property of D systems. If A and B are in D and A is a subset of B, then B minus A is in D. And the third thing we have to check is that D is closed under countable unions yeah, so D has to be closed under countable unions if you take an increasing sequence of sets. But this basically follows from this third assumption. Right, if we have an increasing sequence Sn of elements in D, then we can put Fn equal to the characteristic function of these Sn. And then 3 tells us that this sequence converges to an element of H. But the limit of this sequence is the characteristic function of the union of all the Sn. So 3 tells us that the characteristic function of this union is an element of H. Which means that this union is an element of D, by definition of D. Yeah, so really each point follows immediately from the assumptions that we made. Okay, so this implies that D is a D system. And now let's go back to what we had. So we knew that D was a subset of the sigma algebra generated by A, by definition. And we know that A is a subset of D. So because D is a D system that contains A, D also contains the D system generated by A, right? But now, by Dynkin's lemma, because A is a pi system, the D system generated by A is equal to the sigma algebra generated by A. That was the statement of Dynkin's lemma. Okay, but now, and sigma of A in our notation was just capital sigma. Right? So from this we know that D contains sigma, and D is included in sigma by definition. So D has to be equal to sigma. And now let's look at the definition of D again. If D is equal to sigma, then this just means that this property chi-s in H holds for every s in sigma. Okay, so this is a good start. So now really these characteristic functions, not only the ones of elements in A are in H, but characteristic functions of all measurable sets are in H now. And now we can use these to build simple functions, and we can use these to approximate measurable functions to get the statement. Okay, so characteristic functions are in H. That's going to fit over here. So this implies that simple functions are in H just because H is a vector space. And then we can use this third assumption again. And for Fn, take a sequence of simple functions that converges to a measurable function. For every measurable function, there exists such a sequence. We know that from previous results. So every measurable function can be written as such a limit of elements in H, and therefore every measurable function is in H by this third assumption. At least the non-negative ones. bounded, sorry. And well, now that we know that bounded non-negative measurable functions are in H, every measurable function can be written as the difference between two non-negative measurable functions, right? Just take the positive part and the negative part. So again, because H is a vector space, it contains all bounded measurable functions. And that's exactly what we wanted to prove. So really these three conditions are strong enough to force H to contain all bounded measurable functions. Okay, so this is the monotone class theorem. On problem sheet 9, I think on problem sheet 10 there's an exercise where you can apply the monotone class theorem, and you can see kind of how useful it can be to prove certain things. So are there any questions about this proof? Okay, if not, then this concludes section 6. Yeah.
Would we use the fact that the function has to be bounded?
So from the beginning, H was a subset of H was a subspace of the space of bounded functions on X.
Mm.
So H can only contain bounded functions. But what if H?
Yeah, I mean.
Yeah, what if H contains functions which are not necessarily bounded? So this thing about D systems should still go through.
You can't make the jump from simple functions to just like an arbitrary measurable functions with 3, because 3 says they need to be bounded for you to.
Sure. I mean, that's certainly one reason. But then, what if you omitted this in the assumption? That would be a stronger assumption, yes, but I can't see why this wouldn't go through. So one thing we used was the fact that every measurable function every non-negative measurable function can be approximated from below by simple functions, but that's still true for unbounded functions. So if you
unbounded, then you lose this vector space, right? Because you wouldn't be able to.
Okay, that's one reason. Not really. I mean, you mean if the function is allowed to be infinite somewhere, then you can't subtract two functions because it will have infinity minus infinity. Well, but it could still be finite valued everywhere and unbounded at the same time. Something like x squared. So at the moment I can't see why this would not go through if you don't take bounded functions, if you remove the boundedness everywhere basically. But I'll check. I might be missing something. So yeah, I'll tell you next time. Yeah, I have to check. So yeah, are there any more questions before we start the next section? Okay. So the next section is section 7, product measures. And iterated integrals. And the first subsection is product Sigma-algebras and product measures. And as always, we start with the definition. Let x, comma, sigma x and y, comma, sigma y be measurable spaces. Then the product sigma algebra which is denoted sigma x cross sigma y on x times y is defined as the sigma algebra generated by sets of the form A times B, where A is in sigma x and B is in sigma y. So the sigma algebra generated by sets A times B such that A is in sigma x and B is in sigma y. And these products A times B are sometimes called measurable rectangles. So be careful, even though the notation has this cross between sigma x and sigma y, the product sigma algebra is not the Cartesian product of sigma x and sigma y. It is by definition, the sigma algebra generated by these sets. So x times y denotes the Cartesian product of x and y, but sigma x times sigma y denotes this sigma algebra. Okay? Okay, and the next definition is slightly technical. Let x be a set and let yi comma sigma I be any family of measurable spaces and let fi be functions from x to yi. Yeah, just be a family of functions. And now the definition is then the sigma algebra generated by the fi is by definition the sigma algebra generated by the sets fi inverse of S such that I is in I and S is in sigma I. Okay, so the new thing that we're defining is the sigma algebra generated by a set of functions, and it's defined as the sigma algebra generated by these pre-images of the fi. Okay, so you just take measurable sets in these sets yi, and then take all the pre-images of such sets, and then you take the sigma algebra generated by these pre-images. And that you call the sigma algebra generated by fi. And then there's one remark that gives a connection between these two definitions. If we have two sets, x and y, and we denote by pi x the projection onto the first variable, so pi x of x comma y is just equal to x, and we do the same for y, so pi y goes from x times y to y, and pi y of x comma y is equal to y. Let these be the projections. then one can show that sigma x times sigma y is the sigma algebra generated by these two functions pi x and pi y. Right, so these pi x and pi y, yeah, if you look at this situation, this is one example for the situation of definition 7.2, right? The domain of pi x and pi y is the same for both functions, as is the case in this definition, and then the target spaces are different. Here it's x and here it's y. So we can apply this definition 7.2, and then the sigma algebra generated by pi x and pi y is well defined, just this set. And then if you think about it, if you sit down and think about it, you can realize that this definition gives the same as this original definition of the product sigma algebra. Okay. Now comes the first lemma. So maybe I should say what the final goal is maybe. So the goal is to, if you have two measure spaces and you take the Cartesian product of the underlying sets, then we want to be able to define measures on this product sigma algebra in terms of the measures on x and y, and then we want to be able to define integrals and study these and so on. So now what we've done is we've defined a natural notion of sigma algebra on this product space, and now what we're going to do next is study measurable functions on this product sigma algebra, and then we're going to introduce a natural measure on this product sigma algebra, and then we're going to study integrals and so on. So this first lemma has to do with measurability. So let x comma sigma x and y comma sigma y be measurable spaces. And f x from x times y to the extended real line be sigma x times sigma y measurable. Then if we fix the second variable and consider f as a function of the first variable, then that function is sigma x measurable for every y in y, and the same is true if we fix the first variable. Okay, so this is already nice. So we know if we have a function which is measurable with respect to this product sigma algebra, then we know if we fix one variable, then that function is measurable on x or on y. And to prove this, we first show that the inclusion maps from x to x times y and from y to x times y, that these maps are measurable in a suitable sense. So fix a point y in y. And denote iota y from x to x times y. So this is this index is a lowercase y. So this y is equal to this y that we've chosen. So let this function iota y be defined to be iota y of x equals the pair x comma y. Right, so it just takes the set x and puts it into this product x times y. And first we're going to prove the following claim. This function iota y is sigma x times sigma y measurable. Right, so this makes sense. This function goes from x to x times y. On x we have the sigma algebra sigma x, and on x times y we have the product sigma algebra. So it makes sense to talk about measurability of iota y in this sense. And now we'll prove the claim. Okay, if we go back to the definition of measurability, what do we have to prove? We have to prove that the pre-images of sets in this product sigma algebra are elements of sigma x. So we need to show iota y inverse of S is in sigma x for every S in sigma x times sigma y. Okay, and we're going to do this by a very similar strategy to the proofs in section 6. Namely, we define the set. We define a set which we call C, which is the set of all S where this is satisfied, this measurability condition. So C is the set of all S in sigma x times sigma y, such that iota y inverse of S is in sigma x. And now what we want to show is that C is in fact equal to sigma x times sigma y. So by definition, that's a subset of sigma x times sigma y, and we want to show that it's in fact equal. So what we know already is that C is a sigma algebra because you proved this on the first problem sheet of this lecture. Right? This, sets of pre-images of sets in a sigma algebra, that's again a sigma algebra. That was one of the exercises on sheet 1. And second, all the measurable rectangles are already contained in C, and that's because iota y inverse of such a measurable rectangle, A times B, is just equal to A if y is in B and equal to the empty set otherwise. Right? Because iota was just a projection onto the first, was just this inclusion at the point y. So, yeah, the pre-images of such sets are always measurable because they are either equal to A or equal to the empty set. Okay, so we know two things. C is a sigma algebra, and the measurable rectangles are contained in C. But now this immediately implies that well, C is a sigma algebra that contains the generator of sigma x times sigma y, right? Sigma x times sigma y was just defined as the sigma algebra generated by measurable rectangles. So if I have a sigma algebra that contains a generator of this, then this sigma algebra C must contain the sigma algebra generated by these measurable rectangles. So just from these two facts, we know that sigma x times sigma y must be a subset of C. And this, together with the definition of C, implies that C is in fact equal to sigma x times sigma y. So this proves the claim. Right, the claim was this inclusion map is measurable, and now we know that this claim is true. And now we're going to study measurability of this function where we keep y fixed and consider f as a function of the first variable. Okay, so if this inclusion map is measurable, then if we take a real number alpha such that then the set of x in X such that f of x comma y is larger than alpha. Right, this was the condition for measurability of functions which map to the real line.